In this video, we'll see different potential choices for the activation function of a neuron. So we've seen previously the computation that is made in the neuron, and we saw that it involved this G function, which we call the activation function. So here we'll just see different popular choices for activation functions in neural networks. A first choice is to simply use a linear activation function. So in this case, the activation function G takes its pre-activation and simply outputs it. So if we were to plot this activation function, you'd get a straight line like this. So it doesn't perform any squashing of the input. That is, it takes the input and reproduces it, so it won't be upper bounded or lower bounded. And partly for that reason, it's not very interesting. It doesn't introduce any nonlinearities in the computation of the neuron, which might be useful for performing more complicated computations. A more interesting choice is the sigmoid activation function. So it takes this form, so we'll sometimes note it as with the acronym SIGM and for short. And it simply takes the pre-activation and it computes this formula here. So it's 1 over 1 plus the exponential of minus the pre-activation. And so if we draw this function, what we see is that it will squash the neuron's pre-activation between 0 and 1. So we see that all output values are between 0 and 1 here. And so the bigger the pre-activation, the more it will saturate towards 1, and the smaller the activation towards minus infinite, the more it will saturate towards 0 instead. So this neuron is always positive because it's always strictly greater than 0. It's bounded, that is the output of the neuron. The activation of the neuron cannot be smaller than 0 nor greater than 1. And this activation function is strictly increasing. That is, the bigger the pre-activation, the higher the activation of the neuron will be. Another popular choice is the hyperbolic tangent, or TANH. So it's TANH for short. And it's slightly more complicated. It also involves some exponential. So one form is this form here, where it's the exponential of the pre-activation minus the exponential of minus the pre-activation, divided by the sum of the exponential of the pre-activation plus the exponential of minus the pre-activation. And it can also be written in this form, which is more convenient because it computes just one exponential, so which is reused here, so it might be more computationally efficient. And this is just obtained by multiplying by the exponential of the pre-activation at the numerator and the denominator of this formula here. So if we plot this function, we see that now we get an output which is constrained between minus 1 and 1. So this neuron will say that it squashes the neuron's pre-activation, so this should be pre-activation here, between minus 1 and 1. So it can be positive or negative. It's also bounded, similarly like the sigmoid activation function, and it is also strictly increasing. And the final popular choice for the activation function is what is called the rectified linear activation function. So we noted reclin for short, and it's simply the maximum between 0 and the pre-activation. And so if we plot it, we get a straight line here, like a linear function, if the input is positive, is greater than 0, and otherwise it's just 0. So it's a straight line, horizontal line, and if the input is negative, it always outputs 0. So here it's only bounded by below by 0, so it's always non-negative. It's not upper bounded because the greater the pre-activation here, the greater the output will be. So this can grow, this always grows and can converge to, the output can converge to or diverge towards infinite if the input goes towards the infinity. And in practice, we see that it tends to give neurons that are sparse, that have sparse activity, activities. What we mean by that is that it tends to get neurons that are often exactly zero, which was not the case for the sigmoid or the tanh. The sigmoid or the tanh need to have pre-activations that are exactly a particular value. So in the sigmoid case, to get zero, it needs to be minus infinite, so it doesn't happen really. And for the tanh to be equal to zero, the pre-activation needs to be exactly zero. In this case, there's this whole range of pre-activations which will output exactly zero. So for this reason, we often get zeros as the activation of the neuron across many different inputs. And so we'll say that for that reason, this neuron will have sparse activations or sparse activities. And so those are the 4 different choices, popular choices for the activation function of a neuron.